August 22nd, 1943. School of Tank Technology, Chobham, England. The war in Europe is raging, but here, in a quiet lab, Dr. Robert Stevenson is about to uncover a secret that will change the way the Allies fight the Tiger tank. On his workbench sits a failed transmission gear from a captured WWII. It's a massive piece of steel, 8 inches across, 2 inches thick, designed to transfer 700 horsepower from the Maybach engine to the tank's drive sprockets. But this gear is broken, not worn, not cracked, sheared clean through. A fracture so sharp and sudden, it looks almost surgical. This isn't the first failed Tiger transmission Stevenson has seen. It's the 7th. Every Tiger tank the British have captured and shipped to Chobham arrives with transmission damage. Some are minor, but many are catastrophic. This one is the worst yet. The entire final drive assembly is destroyed, metal fragments scattered throughout the gearbox. The failure was so violent it locked the drive sprockets, immobilizing the tank and turning it into a stationary pillbox. That's how British forces near Tunis captured it in May 1943, abandoned, unable to move, its crew gone. Intelligence reports are clear. Tiger transmission failures are not rare, they're routine. More Tigers are lost to mechanical breakdown than to enemy fire. The numbers are staggering. Of the roughly 2,300 Tigers produced by August 1943, fewer than 700 are operational. The rest are broken down, waiting for parts, or abandoned because repair is impossible. The Tiger was supposed to be Germany's answer to Soviet heavy armor, invincible, unstoppable, armed with the legendary 88mm gun, armored with 100mm of steel, powered by a 700 horsepower engine. On paper, it's the most formidable tank in the world. In practice, it can't always reach the battlefield. Stevenson is a metallurgist. Before the war, he worked for Vickers Armstrong, analyzing steel for naval construction. When the war started, the British War Office recruited him to analyze enemy armor and weapons. He's seen Panzer IIIs and IVs, both destroyed and intact. German tanks are usually well-engineered, reliable. Their transmissions function adequately. But the Tiger is different. Its transmission is a disaster. German designers created a tank that their own industry couldn't reliably support. The result, a weapon system that fails mechanically before it can engage the enemy. Stevenson's job is to find out why. He starts with the failed gear, examining the fracture surface under magnification. The brake is brittle. No plastic deformation, no ductile tearing, just a clean snap through the material. This means the steel failed suddenly under stress with no warning. One moment the gear was transmitting torque, the next it shattered. He measures the gear's hardness using a Rockwell tester. The reading is 62 HRC, extremely hard, harder than the specification for transmission gears. Transmission gears should be around 58-60 HRC, hard enough to resist wear, soft enough to resist brittle fracture. This gear is too hard. Stevenson tests multiple locations. Surface hardness is consistently 62-64 HRC. He cuts the gear in half and tests the core, 52 HRC. The surface is much harder than the core, indicating case hardening, a process where the surface is hardened while the core remains softer and tougher. This is normal for gears, but the case depth and hardness must be controlled precisely. Too much surface hardness creates brittleness. The gear will shatter under shock loads. This Tiger gear has excessive surface hardness. The case is too hard and too deep, 4 millimeters deep, when normal case depth for gears this size should be 2 to 3 millimeters. The excessive case depth and hardness make the gear brittle, prone to fracture under heavy loads. Stevenson needs to understand the microstructure. He cuts samples from the gear, polishes them to a mirror finish, etches them with nitric acid to reveal the grain structure, and examines them under a metallurgical microscope at 500x magnification. The microstructure shows martensite, a very hard, brittle phase of steel formed by rapid cooling from high temperature. Martensite is desirable in controlled amounts, providing hardness, but excessive martensite without adequate tempering creates brittleness. Stevenson sees almost pure martensite in the case. Very little tempered martensite, very little retained austenite. The steel was hardened but not adequately tempered afterward. Tempering is a heat treatment that reduces brittleness. The hardened steel is reheated to a moderate temperature, allowing some of the martensite to transform into tempered martensite, softer, tougher, less brittle. Proper tempering is essential for gears. It provides the balance of hardness and toughness needed to survive shock loads. This gear shows inadequate tempering. The martensite is untempered, brittle, ready to fracture. Stevenson examines 6 more failed Tiger gears. All show the same pattern: excessive surface hardness, deep case depth, untempered martensite, brittle fracture. The problem is not isolated to one gear or one transmission. It is systemic. Every Tiger transmission uses gears with inadequate heat treatment. The gears are too hard and too brittle. They will fail under the stress of normal operation, especially under the extreme stress of combat maneuvering. Sharp turns, sudden acceleration, abrupt stops. Properly treated gears can absorb these shocks. The Tiger gears cannot. They shatter. Stevenson writes a preliminary report dated August 28, 1943. The report documents the metallurgical analysis, describes the excessive hardness, explains the inadequate tempering, and estimates the operational impact. The conclusions are significant and damning. Tiger transmission gears will fail under shock loads encountered during combat maneuvering. The failure mode is catastrophic, sudden fracture with no prior warning. Once fracture initiates, the transmission becomes inoperable. The tank is immobilized. But how did this flaw go unnoticed in Germany's vaunted engineering system? And what did British commanders do with this knowledge? In the next section, we'll follow Stevenson-ES report as it reaches the front lines and see how a secret weakness in the Tiger ES gears became a weapon for the Allies. Stevenson's report didn't just sit on a shelf, it landed on the desk of Major General Percy Hobart, commander of the British 79th Armoured Division and one of the most innovative minds in Allied armor. Hobart understood that defeating enemy tanks wasn't just about firepower, it was about exploiting every weakness, mechanical or otherwise. When he read Stevenson's findings, he saw an opportunity. The report was classified secret and distributed to a select group of armor commanders. It included a simple but radical recommendation. When engaging Tiger tanks, Allied crews should force them to maneuver aggressively. Flanking attacks, rapid position changes, and situations requiring the Tiger to turn sharply or reverse direction would stress the transmission and increase the chance of catastrophic failure. In other words, you didn't always have to destroy a Tiger with a shell. You could break it by making it move. At first, some commanders were skeptical. Tanks are designed to move after all. The idea that you could defeat a Tiger by forcing it to drive seemed absurd. But the evidence was mounting. In Italy, in Sicily, and later in Normandy, British tankers began to notice a pattern. Tigers that maneuvered aggressively sometimes just stopped, not destroyed, not burning, just dead in the water. Crews would abandon them, and later examination would reveal shattered gears and locked transmissions. The pattern repeated itself across the front. In October 1943, British tank commanders in Italy reported Tigers immobilized after sharp turns or sudden reversals. In Normandy, the same thing happened. German after-action reports described transmission failures during combat, often attributing them to poor maintenance or lack of spare parts. But the real cause was hidden in the steel itself, a flaw that no amount of field repair could fix. Stevenson's analysis was clear. The problem was systemic, not a one-off manufacturing defect. Every Tiger transmission he examined showed the same excessive hardness, deep case depth, and brittle, untempered martensite. The gears were ticking time bombs, waiting for the right stress to shatter them. But why had this flaw crept into Germany's most advanced tank? Stevenson dug deeper, reviewing captured technical documents and interviewing German engineers. The answer was a combination of desperation and pressure. Germany's war machine was running out of time, skilled workers, and resources. Production schedules were compressed, and heat treatment, a process that should take hours, was rushed or skipped. Forced laborers and undertrained workers followed simplified procedures, often skipping the crucial tempering step to save time. The result: gears that were hard but brittle, strong but doomed to fail. The consequences were devastating. By early 1944, Tiger transmission reliability was so poor that German tank units began requesting different tanks: Panthers, Panzer IVs, anything but Tigers. The Tiger, once the pride of the Wehrmacht, had become a liability. It broke down more often than it fought, consuming spare parts and maintenance hours the Germans couldn't afford. For the Allies, this was a gift. Hobart's tactical recommendations spread quietly through the ranks. Tank crews were trained to force Tigers into sharp turns, to attack from multiple directions, to create chaos and stress on the enemy's transmissions. The goal was to make the Tiger's own power its undoing, and it worked. Some Tigers were defeated without a shot fired, immobilized by their own gears, abandoned by their crews, and captured by advancing Allied forces. Stevenson's work didn't just influence tactics. It changed the way the Allies thought about enemy equipment. It was a reminder that even the most fearsome weapons could have hidden weaknesses, and that understanding the science behind the steel could be as important as any gun or shell. But what did the Germans know about their own problem? And how did the pressures of war lead to a collapse in quality control across the entire German war machine? In the next section, we'll go inside the factories and hear from the workers who built the Tiger's fatal flaw. While British tank crews were learning to exploit the Tiger's mechanical weakness on the battlefield, the real story of the Tiger's fatal flaw was unfolding far from the front lines, in the factories, foundries, and heat treatment shops of wartime Germany. Here, under the relentless pressure of war, the seeds of the Tiger's downfall were sown, not by enemy fire, but by the very hands that built it. The Tiger's transmission was a marvel of engineering on paper. Designed to handle the massive torque of the Maybach engine and the tank's 56-ton weight, it was supposed to be nearly indestructible. But as Dr. Stevenson's metallurgical analysis revealed, the gears inside were anything but. The problem wasn't just a single bad batch or a careless worker. It was a systemic failure, rooted in the way Germany's war industry was forced to operate as the conflict dragged on. By 1943, Germany was fighting a war on multiple fronts. The demand for tanks, planes, and guns was insatiable. Factories ran around the clock, often with 12-hour shifts and minimal breaks. Skilled workers were being drafted into the army, replaced by forced laborers from occupied countries and barely trained replacements. The pressure to meet production quotas was immense. Supervisors pushed for more output, faster turnaround, and higher numbers, no matter the cost. Heat treatment, the process that gives steel its strength and toughness, became a bottleneck. Proper carburizing and tempering of gears required time, precise temperature control, and skilled oversight. But time was in short supply, and so were skilled workers. Furnaces were overloaded, cycles were shortened, and the crucial tempering step was often skipped or rushed. The result? Gears that were hard on the surface but brittle throughout, prone to shattering under the shock loads of combat. Captured German technical documents and post-war interviews with factory workers paint a grim picture. Gears were carburized and quenched, but not always tempered. The process that should have taken 16 hours was compressed to 8. Quality control was sacrificed for speed. One Czech forced laborer, Josef Novak, later recalled, "We knew the gears were not right. The color was wrong after quenching. But we said nothing. We were not German. Why should we care if German tanks broke down? Better that they break than kill people." Novak's testimony reveals another layer to the story: quiet sabotage. Some workers, resentful of their forced labor and the Nazi regime, deliberately allowed quality to slip. They didn't need to smash machines or set fires. Just letting the process drift, not reporting problems or skipping a step, was enough to ensure that the gears would fail later, far from the factory floor. German supervisors were not blind to the problem. Field reports from tank units described transmission failures, gears shattering, and tanks immobilized in the middle of battle. The Waffenamt, Germany's weapons procurement agency, documented the issues, recommended improved procedures, and called for better quality control. But the system was too rigid, too pressured, and too desperate to change. The priority was always more tanks, faster. What happened after delivery was someone else's problem. The result was a production line that looked efficient on the surface, but was riddled with hidden flaws. Gears came out of the furnace hard, shiny, and seemingly perfect. They passed acceptance tests under light loads, but under the stress of combat, Sharp turns, sudden stops, rapid acceleration, they shattered without warning. The Tiger's greatest strength, its power and weight, became its undoing. By early 1945, the problem was so severe that German tank units began to request different vehicles. Panthers and Panzer IVs, though less heavily armored, were more reliable. The Tiger, once the pride of the Wehrmacht, had become a maintenance nightmare. Crews dreaded the thought of being stranded in no man's land, their tank immobilized by a broken gear, waiting for a recovery team that might never come. The psychological impact on German crews was profound. They had been told the Tiger was invincible, a triumph of German engineering. Now they found themselves betrayed by their own industry. Every mission became a gamble. Would the transmission hold, or would it fail at the worst possible moment? The sense of confidence and superiority that had once defined the Tiger units was replaced by anxiety and cynicism. This sense of betrayal is echoed in the memoirs of commanders like Otto Carius, who led Tiger units on the Eastern Front. Carius wrote of his frustration with constant breakdowns of Tigers abandoned because they could not move, and of the realization, years later, that the problem was not just bad luck or poor maintenance, but a fundamental flaw in the way the tanks were built. "We trusted our lives to machines that were fundamentally defective," he wrote, "not because of enemy action, but because of inadequate manufacturing." The story of the Tiger ES transmission is a case study in how war can break even the best designed machines. It's a story of how pressure, desperation, and the need for speed can undermine quality, and how small acts of neglect or sabotage can have enormous consequences. It is also a reminder that the people who build the weapons of war, whether by choice or by force, can shape the outcome as much as those who use them. After the war, Allied technical teams systematically examined German production facilities, interviewed workers, and documented the processes. They found the same story everywhere. Heat treatment cycles shortened, tempering skipped, quality control sacrificed for numbers. The gears were hard, but wrong. The tanks looked impressive, but they were doomed to fail. Stevenson's analysis became part of the institutional knowledge that shaped post-war tank design. British engineers, learning from the Tiger's failure, specified precise heat treatment procedures, mandatory tempering, and rigorous quality control for their own transmissions. Modern tanks, from the Centurion to the Challenger, owe their reliability in part to the lessons learned from the Tiger's downfall. But what about the battlefield? How did Allied commanders use this knowledge to their advantage, and what did it mean for the outcome of the war? In the next section, we'll see how the Tiger as hidden weakness became a weapon in the hands of its enemies, and how understanding metallurgy helped win the war. By late 1943, the Tiger's reputation as an unstoppable juggernaut was already being quietly undermined by its own mechanical heart. Thanks to Stevenson's metallurgical analysis and the British War Office's willingness to share the findings, Allied commanders now had a new weapon in their arsenal: knowledge. And in war, knowledge is power. Major General Percy Hobart's classified report didn't just sit in a file. It was circulated to tank commanders with a simple, radical recommendation. Don't just try to destroy a Tiger with firepower. Force it to move. Make it turn, accelerate, and reverse. Every maneuver, every sharp turn, every sudden stop would stress the brittle gears in the Tiger's transmission. The more the Tiger moved, the more likely it was to break itself. At first, some Allied tankers were skeptical. The idea that you could defeat a tank by making it drive seemed almost laughable. Tanks are built to move, after all. But as the Allies put the theory into practice, the results spoke for themselves. In Italy, in Normandy, and across the battlefields of France, British and American tankers began to notice a pattern. Tigers that maneuvered aggressively often just stopped. Not destroyed by a shell, not burning, just dead in the water. Crews would abandon them, and later examination would reveal shattered gears and locked transmissions. The new tactics spread quickly. Allied tank units were trained to attack Tigers from multiple directions, to force them into sharp turns and rapid position changes. Flanking maneuvers became more than just a way to get a shot at the Tiger's weaker side armor. They became a way to break the tank without firing a shot. The goal was to create chaos, to make the Tiger's own power its undoing. Reports from the field confirmed the effectiveness of the new approach. In the Italian campaign, British tank commanders reported that Tigers often broke down during engagements, immobilized by their own transmissions. In Normandy, the same thing happened. German after-action reports described transmission failures during combat, often blaming poor maintenance or lack of spare parts. But the real cause was hidden in the steel, a flaw that no amount of field repair could fix. The psychological impact on German crews was profound. The Tiger, once a symbol of invincibility, became a source of anxiety. Tank commanders who had once relied on their armor to protect them now found themselves worrying about every turn, every maneuver. The sense of confidence and superiority that had defined the Tiger units was replaced by caution and doubt. Allied tankers, on the other hand, gained a new sense of confidence. They knew that even if they couldn't penetrate the Tiger's armor, they could still defeat it by forcing it to move. The myth of the invincible Tiger was shattered, not by a bigger gun, but by a deeper understanding of how machines work under stress. This new approach to tank warfare had a ripple effect across the battlefield. German tank units, aware of their vulnerability, began to change their tactics. Tigers were used more defensively, deployed in static positions or as mobile pillboxes, rather than as spearheads for armored assaults. The aggressive, fast-moving panzer tactics of the early war gave way to a more cautious, defensive posture. The impact was felt all the way up the German chain of command. Requests for replacement transmissions and spare parts skyrocketed. Maintenance crews were overwhelmed, and operational readiness rates for Tiger units plummeted. By early 1945, some German tank commanders were requesting Panthers or even older Panzer IVs instead of Tigers, simply because they were more reliable. The Tiger's transmission flaw became a weapon in the hands of its enemies. Allied commanders learned to exploit it, and German crews learned to fear it. The tank that was supposed to dominate the battlefield had become a liability, a machine that failed more often than it fought. But the story didn't end there. The lessons learned from the Tiger's failure would shape the design of future tanks, both in Germany and abroad. British engineers, for example, made transmission reliability a top priority in post-war tank development. Heat treatment procedures were specified precisely, tempering was mandatory, and quality control became rigorous. The mistakes of the Tiger would not be repeated. The Tiger's downfall is a powerful reminder that war is not just about firepower and armor. It's about understanding the machines you fight with and against. It's about knowing that even the most fearsome weapon can be undone by a hidden flaw. And it's about the power of information, analysis, and adaptation. Rehook. But what did the Germans themselves think about these failures? How did tank crews and engineers react as the truth about the Tiger's transmission spread? In the next section, we'll hear from the men who fought in and built the Tiger, and see how their experiences shaped the post-war world of armored warfare. As the war dragged on and the Tiger's reputation for mechanical failure became impossible to ignore, German tank crews and engineers found themselves caught in a web of frustration and betrayal. The Tiger had been sold to them as the ultimate weapon, a tank that could dominate any battlefield, outgun any enemy, and bring victory to the Reich. But for those who fought in them, the reality was far more complicated. Tank commanders like Otto Carius, who led Tiger units on the Eastern Front, wrote in their memoirs about the constant struggle to keep their tanks running. Carius described how his unit's operational readiness never exceeded 60%. At least 4 out of every 10 Tigers were always broken down, usually with transmission problems. Every mission was a gamble, he recalled. Would the transmission survive? Would the gears hold? Or would we be stranded, helpless in the middle of a battle? For the crews, the sense of betrayal was personal. They trusted their lives to machines that, unbeknownst to them, were fundamentally flawed. The breakdowns weren't just bad luck or poor maintenance. They were the result of rushed production, inadequate heat treatment, and a system that valued numbers over quality. "We were told the Tiger was invincible," one veteran later wrote. "But we found it was fragile. We were told German engineering was superior, but we found it was compromised." The psychological toll was immense. Crews who had once felt invincible now lived in constant fear of mechanical failure. Every mission began with a silent prayer that the transmission would hold. Every breakdown was a blow to morale, a reminder that the enemy wasn't always across the battlefield. Sometimes it was inside the tank itself. Engineers and factory workers felt the pressure too. Many were aware of the shortcuts being taken, the corners being cut. Some, like Czech forced laborer Josef Novak, even admitted to quiet acts of sabotage, letting the process drift, skipping steps, or simply not reporting problems. "We knew the gears were not right," Novak said, "but we said nothing. We were not German. Why should we care if German tanks broke down?" Supervisors and managers were caught in the middle. They received reports from the front about transmission failures, but the pressure from above was relentless. More tanks, faster production, higher quotas. Quality control was sacrificed for speed. The process that should have taken 16 hours was compressed to 8. The result was a production line that looked efficient on the surface, but was riddled with hidden flaws. After the war, Allied technical teams confirmed what Stevenson and others had discovered. The Tiger's transmission gears were consistently too hard, inadequately tempered, and prone to brittle fracture. The problem was never fixed. The industrial system that created it couldn't be reformed. The Tiger's downfall was not just a failure of engineering, but a failure of organization, leadership, and priorities. The lessons learned from the Tiger's failure had a profound impact on post-war tank design. British and American engineers made transmission reliability a top priority. Heat treatment procedures were specified precisely, tempering was mandatory, and quality control became rigorous. Modern tanks, from the Centurion to the M1 Abrams, owe their reliability in part to the lessons learned from the Tiger's downfall. For German veterans, the realization that their tanks were doomed from the start was a bitter pill. Many felt betrayed by their own industry and leadership. The Tiger, once a symbol of pride, became a symbol of what happens when ambition outpaces reality. "We trusted our lives to machines that were fundamentally defective," Carius wrote, "not because of enemy action, but because of inadequate manufacturing." The Tiger's story is a cautionary tale for engineers, commanders, and anyone who builds or relies on complex systems. It's a reminder that the smallest flaw, hidden deep inside a machine, can have consequences far beyond the factory floor. It is also a lesson in humility, a reminder that even the most advanced technology can be undone by a single overlooked detail. Rehook, but the Tiger IS transmission wasn't the only German engineering failure of the war. In the final section, we'll look at how the lessons of the Tiger influenced the design of future tanks, and why understanding the science of steel, heat treatment, and quality control is still crucial for anyone who wants to build machines that last. The Tiger Tank S transmission flaw was more than just a technical hiccup. It was a warning to every engineer, commander, and nation that would ever build a tank again. As the war ended and the world moved into a new era of armored warfare, the lessons learned from the Tiger S downfall became a blueprint for how to and how not to design machines meant to survive the chaos of battle. After the war, Allied technical teams fanned out across Germany, examining factories, interviewing workers, and dissecting every piece of captured equipment. What they found confirmed everything Dr. Stevenson and his colleagues had discovered at Chobham. The Tiger S transmission gears were consistently too hard, inadequately tempered, and prone to catastrophic failure. The problem was not limited to one factory or one batch. It was systemic, the result of a production system under impossible pressure. The British, in particular, took these lessons to heart. When they began designing new tanks in the late 1940s and 1950s, transmission reliability was at the top of the list. Heat treatment procedures were specified down to the last detail. Case depth and surface hardness were measured and verified. Tempering was not just recommended, it was mandatory, and every batch of gears was tested for microstructure and hardness before being approved for use. Any deviation from the specification meant the entire batch was scrapped. This rigorous approach paid off. British tanks like the Centurion and later the Chieftain became known for their reliability, even under the harshest conditions. The same was true for American tanks like the M48 and M60 Patton, and later the M1 Abrams. The lessons of the Tiger's failure were built into every gear, every shaft, every transmission. Modern tanks could maneuver aggressively, absorb shock loads, and keep fighting long after their predecessors would have broken down. But the Tiger's legacy went beyond engineering. It changed the way armies thought about quality control, production pressure, and the human element in manufacturing. The story of the forced laborers who quietly sabotaged gears, the supervisors who ignored problems to meet quotas, and the commanders who sent men into battle with machines doomed to fail became a cautionary tale. It was a reminder that war is not just about courage and firepower, it's about the systems that support them. The Tiger's transmission flaw also influenced the way modern armies train and support their crews. Today, tank crews are taught not just how to fight, but how to maintain and diagnose their machines. Maintenance is no longer an afterthought. It's a core part of combat readiness. Quality control is built into every step of the process, from the foundry to the front line. Museums and historians have also played a role in keeping the Tiger's story alive. At the Tank Museum in Bovington, England, Tiger 131, the only running Tiger in the world, is maintained with modern lubricants, careful monitoring, and a deep respect for its inherent weaknesses. The museum's engineers know that the transmission is a relic of a different era, prone to failure if pushed too hard. They operate the tank gently, avoiding the kind of stress that would have shattered its gears in combat. For modern engineers, the Tiger's story is a lesson in humility. It's a reminder that even the most advanced technology can be undone by a single overlooked detail. It's also a call to respect the science of materials, understanding that hardness without toughness is a recipe for disaster, and that every shortcut taken in the factory can become a catastrophe on the battlefield. The Tiger's transmission flaw also had a psychological impact that lasted long after the war. German tank crews who survived the conflict wrote about their sense of betrayal, trusting their lives to machines that were fundamentally defective. The myth of German engineering superiority was shattered, replaced by a more nuanced understanding of the pressures and compromises of wartime production. For Allied crews, the knowledge that the Tiger could be defeated by its own gears was a morale booster. It gave them the confidence to engage, to maneuver aggressively, and to exploit the enemy's weakness. The idea that you could win a battle not just with firepower, but with knowledge, became a core part of Allied doctrine. The story of Dr. Stevenson and the Tiger's transmission is also a testament to the power of technical analysis. Stevenson's meticulous work, measuring hardness, examining microstructure, and documenting every failure, became part of the institutional knowledge that shaped the post-war world. His reports influenced not just tank design, but the way armies think about reliability, maintenance, and the importance of listening to the people who actually use the equipment. Today, every modern tank transmission is a product of these lessons. Gears are heat-treated with precision, tempered to the right balance of hardness and toughness, and tested rigorously before being installed. Quality control is not just a box to check, it's a matter of life and death. The failures of the Tiger are not repeated, because the knowledge gained from those failures has become part of the DNA of every new design. The Tiger story is also a reminder that war is fought not just by soldiers, but by engineers, metallurgists, and factory workers. The outcome of a battle can hinge on the way steel is treated, the way a gear is tempered, or the way a worker follows a procedure. The smallest detail can make the difference between victory and defeat. As you finish this documentary, think about what the Tiger's transmission flaw means for us today. Is it a lesson in the dangers of cutting corners? A reminder that quality matters more than quantity? Or simply a story of how science, engineering, and the human element can shape the course of history? Whatever it is, let it inspire you to look deeper, to ask questions, and to never take reliability for granted. If you've enjoyed this journey through the hidden story of the Tiger tank's downfall, please like, comment, and subscribe for more untold WWII stories and deep dives into the technology and people that shaped history. What do you think is the most important lesson from the Tiger's transmission failure? Share your thoughts below. We love hearing your take. Thank you for joining us on this exploration of engineering, war, and the power of understanding the details. Until next time, keep asking questions, keep learning, and keep remembering the real stories behind the legends.